of that one, okay? So 1 minute per iteration on 512 nodes, but we get a result, converged result in about 30 iterations. So that's the largest calculation. This is presented in this paper that is available on arXiv. We recently put it on arXiv. Rio Yakoda is now at Boston with me. It's my postdoc. He was also my postdoc in my previous employer, Boston, University of Bristol. Tsuyoshi Hamada is collaborating with us in Nagasaki's computing center. J.D. Barton, he's my expert in the application, and he's the one I would have called on the phone if you asked a hard question. Matthew Nepley is from Computation Institute. He was one of the team members of the PETC library development team and is a collaborator of ours for several years on the fast multiple method on both the MPI code and the development of that library, the open source library, and also now on the GPU work. So this paper is available on arXiv. You won't find it, the link on my website today because I haven't updated the website in the last few days when this actually came live. And so I want to end with just one word of open source, and I want to say that to develop new versions of all of these most effective algorithms like the fast multiple method, really the ideal environment is created by the open source model. I want to just leave you with a little plug for that because, like I said, the fast multiple method hasn't had the impact that it could have. And I want to give you the example of molecular dynamics, where the community has a large amount of open source tools, and basically molecular dynamics blossomed when all of these tools started becoming available. Now you couldn't imagine doing molecular dynamics without the availability of all of these tools. I would like to see some of these things happen in other areas, and that can only happen through the collaboration. When these things become very hard, it's not nice that we have to reproduce the work. If it takes you 1 year to code it, it's not nice that you're not sharing it, forcing other people to go through all that pain again. So I'd like to call this the triad of extreme computing. Fast algorithms, which are usually rather complicated, open source, and heterogeneous systems. With these three things together, I think we can really approach extreme scale computing and answer some of these questions that I posed in the beginning of the talk as the vision for computational biology in the future. So that's the end. I'd like to end with a list of acknowledgments there.
Any further questions from the remote site?
I see a hand there.
From UCLA.
Go ahead, UCI.
It looks like your code, the code listing you showed, use simple single precision. And have you compared the result between single and double precisions in your application, the fast multiple method?
Thank you very much for your question, because it gives me the opportunity to point something out, which is also the sort of a paradigm shift in GPU that we have thanks to GPU computing, which is the possibility of incorporating mixed precision for getting the best out of our algorithm. So it turns out that in the fast multiple method, we're already approximating the evaluation in the far field. Okay, so we can do those things in single precision and just do the final aggregation of the results in double precision without any degradation in the final accuracy. Now, of course, with the newest architectures, this is not such a big deal because we're getting more and more double precision performance. With the previous generation, it was big because the double precision, the double precision performance was a lot less than single precision. But we were able to get a double precision result performing most of the far field calculations in single precision. And so we didn't really do the effort of doing everything in double precision and comparing the timings. There wasn't really any point because we were getting already an answer with measurable errors, controllable errors, up to machine precision, doing the far field in single. So again, thank you for your question.
So you are saying that all the multiplication part is done in single precision, and when you aggregate, you did that part in double precision.
That's right. With the reduction, you can do the reduction, final reduction in double precision, and you can do the near field, which is a direct interaction in double precision. I may be leaving some details out. If you have more detailed questions, we can certainly get you the answers of how this is performed in detail, which in every operation needs to be done in double precision. But the kind of high-level answer is that you can do all of your far field in single, and then the final summation at the evaluation point, and your local interactions in double.
Thanks.
Go ahead.
I had an email question from one of the online participants. This is somewhat of a higher level question, so if you need to phone your postdoc, you can. How does the fast multipole method, conceptually, how does that compare with the RETE algorithm, R-E-T-E? Are you familiar with that?
R-E-T-E. R-E-T-E. I actually I'm not familiar with R-E-T-E. RETE algorithm, no. Okay. I'm afraid. But I'll probably be Googling when I get to the R-E-T-E. No, never heard of it. I'm sorry.
CSA has another question.
Hi, thanks for that talk. I have a somewhat more fundamental question. So the electrostatic model you're using is the linearized Poisson-Boltzmann equation. So a lot of times when with highly charged molecules, as you know, you need to keep the exponential term that comes from the Debye-Huckel theory. So I'm wondering what you have to do in those cases. Would you have to switch to a multigrid method? I mean, can you do something with a fast multipole method for any kind of a nonlinear term in there, such as the exponential term that comes from the real Poisson-Boltzmann equation, not the linearized equation that you show, because that might be essential for modeling, as you say, a lot of lysozyme molecules in a cell interacting together, or in particular DNA. DNA is highly charged and thus becomes unstable in the wrong ionic concentration, so you'd have to model the presence of ions in there. So just sort of an open question. Thank you.
Thank you. Oh, as you can imagine, that is a more specific question about the applications. I realize we're using the linearized Poisson-Boltzmann, and if you want to do the nonlinear problem, you can't use the same formulation with the boundary element method that we are using. So we haven't gone into that extension of including the nonlinear effects of the Poisson-Boltzmann. But I can tell you that if you it would be a very interesting research topic to see if you found that you need to keep your nonlinear terms, and such as a method such as the multi-level method would be useful there, or some other method. It would be very interesting to look at combinations of hybrid methods. It's always very interesting when you find a way to combine the best of both worlds, in the sense of using the methods in their happy spot, right? And if you find that a microscoping description is necessary, the fast multiple method could be used in combination with something like a particle mesh representation, because you can use it to solve a Poisson equation on the volume as well. But this is sort of kind of speculative about other uses of fast multiple method that we haven't actually done any work on that or started to look at in detail. And so I'm afraid I can't really answer your question satisfactorily, except for I forgot to say in the beginning of my talk that if I fumble for words, you should blame it on the jet lag. I forgot it, and I proved not to be too tired to get through my talk, so I guess it's a moot point now. And I'd be happy to answer any more questions now or afterwards as well, on email or something, and I'd be happy to. Please do visit our website to find the links to the material, and we'll also provide it to the Google groups that's being maintained for this course, for the summer school. Any more questions?
Let's thank Lorena again.
Thank you.